Hey guys, here is the last video of Unit 7, and it's me explaining what the heck I squished all this stuff on a piece of paper for, and why I think this is a really good reference sheet. So let me explain. If you see here, we need this piece of paper, Unit 7, if and when they ask the question, does the data provide convincing evidence of something? So that's when we want to do this piece of paper. Another thing that would give us, tell us that we need this piece of paper, if they talk about the null hypothesis, or if they ask you to state the null and the alternate hypothesis, then you know, oh, I'm pulling up this piece of paper. Now there's 4 ways they could ask this, and in fact, technically 5 different ways they could ask it. And on the test, they won't ask all 5. They'll probably just ask one of the 5. So let's talk about each of the ways. One could be, we're just doing a one sample z-test for p. So that's like them saying, you talk to some people and you want to know the proportion, the true proportion of people that approve of Trump. That's been on the news a bunch. Approve of Trump. Okay, that's what you'd like to make an inference about, and the accepted truth supposedly is 40%, and you have a sneaky suspicion it's less. You're like, oh, that's weird. Everybody I talk to is not very happy, or maybe you have a sneaky suspicion the other way. So these can go not equal to, greater than, or less than 2. So this would be the case if they said, well, I don't agree or disagree. I think it could be more and it could be less. I just don't think that it's 40% approval rating. So that's when you'd use a not equal to sign. Now in this condition or in this setting, we would want these conditions to be at play. So if that's all I have, I just have one sample, then we need to make sure it's random and we mention it. And if we talk to 500 people, then we need to say it's safe to assume that our population is greater than 5,000 of the people we're interested in making an inference about. We want to do a large counts, right? So we would, if n's 500, we'd do 500 and times p, which is 0.4. We want to make sure that number is greater than or equal to 10, and almost all the time it is. It's super big. And then 500 times 0.6, which is 1 minus 0.4, make sure that's greater than or equal to 10. And in this case, I asked a lot of people, I'm going to be fine. So because this worked out, I know that it is normally distributed. The sampling distribution is normally distributed. So what does it work in my calculator, and how does my calculator come up with a p-value? Well, my calculator comes up with the p-value using this formula and table A, and I normally don't do any of that by hand, but if you type it in your calculator, you'll get a z-score and a p-value, and you should always put those on your test. I've noticed though on these sample ones, not a lot of people are having you this year and this year only calculate these. But if you needed to, the calculator, it's the 5th button, it's your 5th choice when you go to stat test, a one proportion z test. Okay, now once you get to the end, and I think most of us are pretty good at this by now, we're either going to go through door number 1, right? Door number 1 or door number 2. Either my p-value is less than 0.05 or it's greater than or equal to 0.05. So door number 1 would say, that's the one I'm hoping for, because then I could say we reject the null hypothesis. Our sneaky suspicion was right. We do have sufficient evidence to support that the proportion of, I use the one from StatMedic, that the proportion of popcorn is less than 40% caramel. Okay. Now, let's say our p-value is something bigger than 0.05. We'd have to fail to reject the null. We do not have sufficient evidence to support that the proportion of popcorn is less than 0.4. So the reason why I write that here is that's literally I'm going back to the problem and I'm repeating this in words. Okay, that's it. That's how you do a significance test. We've done this, we've done this, we've done this. So what would make it a little bit more difficult? Well, they could have given you two groups. So I think I showed this yesterday in regard to confidence intervals. They could do the same, but instead of asking you to do a confidence interval, we can do a significance test. So again, let's say this is the proportion. Maybe your friend from California is like, I think the approval rating out here for Trump is the same as on the East Coast. And you're like, no, I think East Coast is greater than West Coast. So you would have to define whatever the first group is. If you want the first group to be group 1 East Coast, and then if you want group 2 to be West Coast, you just have to define that. Okay, so make sure you define that. Now, I've gotten a lot of questions recently about why is it sometimes they write it like this and sometimes like they write it like this. Both of these are correct. Mathematically, they're saying the same thing. Think about it. If P1 is 0.40 and P2 is 0.40, then you get 0. And notice 0.40 is equal to 0.40. So mathematically, when you have two numbers equal to each other, if you subtract them from themselves, you get 0. Okay. In the same way, this statement is the same thing as saying that statement, because if you get a number that's bigger than another number, when you subtract it from the smaller, you get a positive number. And this symbol just means is a positive number. So these are saying the same thing. Okay, so how is the condition different? When we look at this situation, we have one extra thing to talk about. Because we have two samples, we want to make sure that the samples in relation to one another are independent from one another. Now, what else would be different? Well, just like you did a 10% condition, let's say in group 1, you asked 400 people on the East Coast. You want to make it safe to assume that there's greater than 4,000 people on the East Coast. And then if you talk to 500 people on the West Coast, you've got to say that it's safe to assume there'd be 5,000 people on the West Coast, right? So you're essentially doing the exact same thing, but you're just doing it to each group. Now, this gets a little technical. It's technically, and StatMed talks about this, technically it's more accurate to do the combined P, but notice she actually used P1, P2, P2, and that would be correct as well. I don't think this is going to come into the test. It's just about being slightly more accurate. And remember, we would just type it in the calculator, and the calculator is going to do this for us. So once again, the formula that your calculator is actually doing P combined, and you're just getting these data values from your calculator. So what would be the calculator button you would push? This, instead of the 5 button, it's the 6 button, because that's a 2 proportion z-test. Now let's take a look at what's different in my conclusion. Same thing, you're going to either have your p-value less than 0.05 or greater than or equal to 0.05. So same thing, door number 1 and door number 2. So the only thing different in my script is to say that we reject the null hypothesis, that's the same. We do have sufficient evidence, that's the same, to support H sub A, that's the same. But notice H sub A is different, right? This is very different. So I have to say that's the part that's different. I have to say that there is a difference. H sub A is that there is a difference in the proportion of the thing that I have. Now, if it's a one-sided test, I could say that it is P1 is greater than P2. Okay, now how do I say that in the conclusion part? When our p-value, when our p-value is greater than 0.05, we say exactly the same way. We fail to reject, we don't have sufficient evidence to support H sub A, and once again, H sub A is that there is a difference in the two proportions of the things I'm measuring. Okay, so that's pretty much just like confidence interval, but with just a slight tweaks, slight differences here. And notice I've only been asking yes or no questions. So let's take a look at what if I actually measured something. So this was an example. Again, let me zoom out just to give a review. So this is if they ask one group a yes or no. This is if they ask two groups a yes or no. All right, these are proportions. If it's a mean question, I'm doing this. This is if I have one group, a mean question, or two groups, a mean question. So let's zoom in. One sample t-test for mu. So if I just had said the true mean time students spend on their homework is 25 minutes a day. Now maybe you have a sneaky suspicion it's greater than 25 minutes, so that is your alternate hypothesis. Okay, now keep in mind they could change this whenever they want, but normally they keep it at 0.05. Okay, so what are my conditions? They look pretty similar to the last time, except I just have one sample, so I don't talk about it in relation to the other sample. I just mentioned that it should be a random sample, or if it's an experiment, there should have random assignment. 10% condition would be the same, right? And now this is the same as the confidence interval. So I want to do one of the three. As long as you have one of the three, then you're going to have approximately normal sampling distribution data. So either the population distribution is normal, or n is greater than or equal to 30 because of the central limit theorem, or you recognize that the sample shows no strong skews or outliers, and you may have to make a quick sketch to show that or explain why you know. All right. And in the formula, this is what comes out of the calculator. And normally we just use a calculator. We don't actually calculate it ourselves. All right, and so why do we need the calculation? We want to find the p-value. And the p-value is the probability of getting that result, at least as extreme, if this experiment was done purely by chance and H sub O is true. Okay, so what kind of calculation is it doing? This is actually the second button under stat test. It's called a t-test, just a plain old t-test. So in our conclusion, we would say exactly the same thing. The only thing different is H sub A is different. So that's the only thing changing each time. That's why the poster works, because essentially we're just substituting in H sub A. So if we go back up to the top, H sub A was that mu is greater than 25. So that's why I say we do have sufficient evidence to support that the mean is greater than 25. Now I want to make sure I do context, so 25 hours of homework, right? Make sure you have context. Okay, now what if you had a p-value that was greater than 0.05? Then once again, you'd fail to reject the null and say you do not have sufficient evidence to support that the mean is greater than 25 minutes per day to do your homework. Keep putting down the context. Okay. What could be different here? So we're going to talk here in a second about a two-sample t-test. And that's when you have two samples, right? Maybe I took population group 1, my 8th period class, and population group 2, my 1st period class. And so you have a sneaky suspicion that the average amount of homework you do is different depending on which class you're in. So we should assume the null hypothesis is that they are the same. Now these are two separate groups, and so you should define your parameter as the two mean of the population 1 and population 2. So what was all this on the video about a difference of means? That's when you have a matched pair. So it might be hard to see that. Let's see if we can zoom in. So in a matched pair design, that could be you, or that could be somebody just like you, or data that's similar enough that we could find a difference. So to know what that is, technically you're only doing one sample, because your one sample data is the difference. So in that regard, notice that you do not have two means, right? You ultimately just have one data point, and it's the average difference between the data sets. So the reason why you would pick this is you say to yourself, does it make sense to find the differences in the data? Each data point, does it make sense to find the difference? And that's when I would use that. And if you're using that, you're going to use this entire column. You will still use it, even though it feels like you have 2. So I would change my parameter to say the true mean difference. And I still just have 1 mu difference, all right? And that's only 1 sample, even though you have 2 pieces of data that go into a single data point. Okay. This would be kind of like a weight loss. Yes, we take your weight before the exercise program and your weight after the exercise program, but we're really only interested in figuring out the average weight lost. So if the average person lost 5 pounds on the diet and you think the average person should have lost something more than 5 pounds, right? See how in that regard, even though you took the before and the after, that's still 1 data point that you're accumulating. All right, so let's keep moving. If you took 2 sample T, you're going to have 2 mu's for your population. And this could be, you could have a sneaky suspicion about one's greater than or less than or just not equal to. And so let's just zoom in on the conditions. The conditions would be exactly the same, but once again, because you have 2 groups, you want to make sure the data is coming from 2 independent samples. And once again, you're going to want to do a 10% condition for both groups. And once again, you're going to want to do this group of 3 techniques, but you got to do it for both samples. So you may have to do a little sketch for both of the little samples there to make sure that there are no strong skews or outliers. Or you might get lucky and they might say both population distributions are approximately normal, so you're good to go. Or you could get lucky and both of the samples N is greater than 30. Okay, so this is the formula they use and the p-value. And here's the calculator used. It's the 4th button, also known as a 2-sample t-test. Okay, so same evidence, and the only thing that changes is H sub A, that there is a difference in the means. And that's what changes each time, that there is a difference in the means. All right. Whew. Last but not least, one of the toughest things on the test is knowing the difference between a type 1 and type 2 error and power. So let's just write down our notes. And if we get a question like this on the test, we're going to use our notes. So Luke gave an example where, what if mu was the true mean weight of a burrito? So H sub O is mu is 8 ounces. And so if that really was true and you actually rejected the null, you would have screwed up. And so screwing up means I made an error, right? So if I make an error, that's called a type 1 error. That's when they tell you that H sub O is true, but accidentally we rejected it. We've made a mistake. Now, what would be a type 2 error? That means you walked through door number 2. You failed to reject the null when in fact you should have. So you've been given that H sub A is true, but you failed to reject the null in the context. I failed to reject that the burrito was 8 ounces. So, how would you calculate powers? They could ask you a couple other questions. So the probability of a type 1 error is always just alpha. And so the probability of this would just be its complement. And the power is actually kind of a difficult probability to calculate. The probability of the power is the probability that you're going to reject the null given H sub A is true. So that can be a complex thing. Normally they won't make you calculate it. And so the probability of a type 2 error is just 1 minus the power. So if they give you the power, you just take 1 minus it. Okay. Now, last 2 things. If they ask you to interpret the power, you're going to say, well, given H sub A is true, the burrito really was undersized, there is a blank probability that we will correctly reject the null, reject that the burrito is 8 ounces. So we want to always throw in the context. Last but not least, and this did come up in the last couple days, what if they ask you, how do I increase the power of the test? You have two choices. You can increase N, and that decreases the standard deviation of the distribution, sampling distribution, which actually increases your likelihood of detecting it. Or you can increase alpha, which is actually a little bit more direct way. You actually will just detect an error that much simpler. So you see that right off the bat. If your p-value is 0.07, if you increased alpha to 0.10, you would be able to reject the null. That's it, guys. Great talking to you. Good luck. See you tomorrow.